It is always helpful when we want to do the network models, check the graph. Now that you want to write the constraint of node 6, it would be much better to check the graph. That is here. And we know all these arcs to 6 are directed ones to this one. So the associated variables are x26, x46, and x56. Similar to the origin, we know that one of these three things must be taken. So we can get to node 6. And another point is that only and only one of them must be taken, not two of them, not three of them, not none of them. So with this hint that I just gave you, try your best to write the constraint. Pause the video and write it. The constraint is this. Three variables, 26, 46, and 56 summation must be equal to 1. Now it guarantees that the results that we get from our math is gonna be one of these things. 1 0 0 0 1 0 and 0 0 1. It's not possible, for example, such a thing because it says summation of all three variables must equal to 1. And now that we are good with this constraint, we can go for the other constraints. Let's write the constraint now for node 2. One point that you should consider about node 2 is that node 2 is not start or it's not origin or destination. It's a transshipment node. And the constraint related to node 2, 3, 4, 5 are gonna be the same. So I'm gonna give you a hint on node 2 so you can write the constraint regarding this node as well as the other ones. Okay, for node 2, since it is a transshipment node, the input flow and or the inflow must equal the outflow like any other transshipment constraint that we have had so far. So let's start for the inflow ones. Okay, we have x12, as you can see, my friends, 1 2 plus 3 2 because we want to write first the inflow constraint, the inflow current. So we have x32 and also we have x42 plus x42. It is all the inflow current, or it is all the inflow to 2 that must equal the outflow of 2. Outflow of 2, we have 2 3 here, as you can see, 2 3. We have 2 4, and also we have 2 6. So it is the constraint that we come up with according, and now I wrote it completely. It is not a hint now, but no problem. Now you are going to continue writing the other ones as an exercise. We still have other 3 transshipment nodes, so you can do them as a practice to make sure you got the point completely. Okay, so about this 1 2 3 2 4 2 equal 2, 3, 2, 4, and 2, 6. In this situation, we are assured that the answers that computer is giving us based on the mathematical model guarantees that inflow and outflow on every transshipment nodes are equal. Now that I solved it completely, not solve it completely, write it completely, just check to make sure everything is fine. In these examples, in this type of modeling, we should always be careful about the typos. Yeah, it seems we did it correct without any typo. 2, 3, 2, 4, 2, 6 equal to, oh, we forgot 1, 2 here. No, it is here. It is here 1, 2, 3, 2, 4, 2, and 2, 3, 2, 4, 2, 6. I just thought I forgot 1, 2 over there. So, yes, 1, 2, 3, 2, 4, 4, and 2, 3, 2, 4, and 2, 6. And similar to the previous examples that we have done together, my friends, this way of writing the constraint is more acceptable, while the other one is completely true. Just let me show you exactly at the point, because usually I get questions on this, that which one is better. They are exactly the same in terms of mathematical modeling, and both of them are correct, but this one that we see here are better in terms of math, because it brings all the variables on the left and the values on the right. So it is considered more prestigious, if I'm correct with the word. But these things that you see here is exactly the same as this when you are writing it on the paper and when you are giving it to your computer to be solved by solver. And today we are gonna solve this model. So the only important things with these things is that you need to make sure that you have covered all the variables and the signs are correct. The reason that we have here minus x12 minus x32 and minus x42 is that it brings all these three variables on the left, brings them to the right. So when it brings them to the other side of equation, their sign is changed from positive to negative, and 2, 3, 2, 4, and 2, 6 are gonna stay on the same place. Okay, now that we have these constraints related to node 3, you are ready to do the same thing for the remaining nodes that are 3, 4, and 5. And to make a perfect practical session, so please pause your video and try your best to write these three constraints on your own. Okay, let's check how well you have done writing the constraints of nodes 3, 4, and 5. Here are the answers. We have 3 nodes and so 3 constraints. The logic is exactly the same as before. The inflow and outflow must be equal. Okay, so here let's go for node 3. For node 3, here 3, 2, 3, 5, they are outflow. So as you can see, from 3 we get to 5 and we get to 2. They are outflow. And on the other side, we have the inflow. 2, 3, that is 1, 3, 2, 3, and 5, 3. that is inflow, and these two things must be the same. The same logic happens to the other one. For example, for the 4, you have the outflow 4, 2, 4, 5, and 4, 6. That must be equal to the inflow, that is 2, 4, and 5, 4. And again, my friend, here you see your textbook has brought everything on one side of the equation. If you have written in your regular way, that's, for example, x13 plus x23 plus x53. Now I'm working on the inflow of 3 because it gets it from 1, get it from 2, and get it from 5. 3 arrows go inside 3 equal the outflow. We have 2 outflow, 3, 2, x. 3, 2 plus x, 3, 5. And 3, 2 and 3, 5. And here we have x3, x2, 3, and x5, 3. The reason I'm writing all these things in this way is to make sure you get a good understanding that none of these math points, negativity, positivity, and bringing them to one side or not, has no effect on the correctness of your model. So we did also the constraint regarding these remaining transshipment nodes. So we did the decision variables, we did the objective function, and we just finished the constraint related to all the nodes, including origin and destination nodes, as well as the transshipment nodes. And the final step is writing the, because we did it, we joined it, and the final step is writing the whole model. You may ask yourself that what about the non-negativity constraints? Since, my friends, the constraints, the variables are 0 and 1 variables, there is no need for non-negativity constraint because the decision variables are already non-negative when you define them. You say they are either 1 or 0. So there is no need for non-negativity constraint where you are dealing with 0, 1 constraint when you define them well like this. So the whole model is this one. Here we have the objective function, and here we have the other constraint, origin, destination, and transshipment nodes. Okay, now we are done with the modeling of shortest route problem that we just had. And when you solve this model, automatically it would tell you what is the best direction from origin to the destination. And with the special way and with the logical way that you define your constraint, you can be sure that when it gives you the answer, you will have a path. For example, you start from 1, go to 3, go to 5, go to 4, and after that go to 6. It is always guaranteed that there is 100% connectivity with the roads. And again, that's a wonderful part of this modeling, that when you solve the model, you get you notice that all the roads are connected, all the suggested roads are connected, exactly like the GPS navigation system that we have. And this session we are gonna solve the model as our classwork.